Find somewhere comfortable, somewhere your body can stop trying. You don't need to follow any of this closely. You don't need to remember a word of it. If you drift partway through and wake somewhere else entirely, that is exactly right. Tonight we are going to think about something very small and very quiet. Something that falls in silence. Something that has been falling in one form or another for as long as there have been cold clouds and winter air above this turning world. We are going to think about snowflakes. Not in a scientific way exactly. Not in a way that requires concentration or effort. More. The way you might think about them if you were standing at a window late at night, watching them come down through the lamplight, each one catching the glow for just a moment before it disappears into the dark below. There is something almost impossible about a snowflake when you sit with it long enough. The idea that something so intricate, so perfectly symmetrical, so quietly beautiful could be assembled without any hands, without any plan, without anything guiding it except the temperature of the air and the slow, patient drift of water molecules finding their place. No architect, no design table, nothing but cold and vapor and time. And yet there it is. Six-sided, exact, unique. Let the day go for a while. Whatever it held, it is already softening at the edges the way all days eventually do. You are here now, in the quiet, and outside somewhere, or in your memory, or in the space just behind your eyes, it might be snowing. We are in no hurry tonight. The flakes, after all, take their time. There is a question that has followed human beings for a very long time, longer perhaps than you might expect. It is a question that sounds simple, almost childish, but which has occupied some of the most remarkable minds in history. Why 6? Why does a snowflake always have 6 sides? Not 5, not 7, not some irregular tangle of angles. Always, without exception, 6. 6 arms reaching outward from a central point, each one a near-perfect mirror of the others. Why should water, falling through cold air, consistently produce this particular shape? This question is old, ancient even. Around 50 years before the Common Era, a Chinese scholar named Han Ying was compiling a collection of observations about the natural world. He noticed something that others around him had perhaps seen but never quite articulated. He wrote about the contrast between flowers, which tend toward 5-sided symmetry, and snow, which tends toward 6. Petals arrange themselves in 5s. Snowflakes arrange themselves in 6s. He set this down quietly, without grand conclusion, and moved on. But the observation remained. It would be nearly 2,000 years before anyone in the Western world looked at a snowflake and asked the same question with the same care. In the winter of 1610, a German astronomer was crossing a bridge in Prague. His name was Johannes Kepler, and he's remembered mostly for working out the laws by which planets move around the sun, those elegant elliptical paths that govern the motion of everything in the solar system. But on this particular evening, crossing that bridge in the cold, a snowflake landed on his coat. He looked at it. He was struck, the way people sometimes are struck by something they have seen 1,000 times but never truly examined, by its shape. 6 sides. Perfect. He could not let it go. Kepler sat down and wrote an essay. He called it Strena sous de Neve Sexangula, which translates roughly as a New Year's gift of hexagonal snow. He presented it as a gift to his patron, a gentle, playful piece of writing that nonetheless contains the first serious scientific attempt to explain why snowflakes have 6 sides. He looked for analogies in the natural world. He thought about the hexagonal cells of a honeybee's hive, the way seeds pack themselves into a pomegranate, the geometry of stacked cannonballs. He could not find the final answer because the tools to find it did not yet exist. But he asked the right question, and asking the right question is often the more important thing. He ended the essay with a kind of beautiful surrender. He did not know why, but he was certain the answer existed, somewhere, waiting. It did. And it had to do with something far smaller than anything Kepler could see. To understand why a snowflake looks the way it does, you have to go very small, smaller than the snowflake itself, smaller than the crystals within it. You have to go all the way down to a single molecule of water. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom. You have known this since school probably. H2O. But there is something in the geometry of that bonding that contains everything we need. The 2 hydrogen atoms attach to the oxygen at a particular angle, not a straight line, not a right angle, but something close to 104 degrees. This specific angle means that when water molecules come together in the cold and begin to form ice, they arrange themselves in a particular pattern. They form rings, 6 molecules to a ring, each one connected to the next by what chemists call hydrogen bonds, those gentle attractive forces between the slightly positive hydrogen atoms of one molecule and the slightly negative oxygen of another. 6 molecules. 6 sides. The hexagonal symmetry of every snowflake that has ever fallen, across every winter this planet has ever had, traces back to that one angle. 104 degrees. Something so small it is essentially invisible, and yet it echoes outward into every crystal, every flake, every field of white that has ever covered the ground in winter. This is where the snowflake begins. Not in the clouds, but in the geometry of water itself. When a snowflake starts to form, it begins with what scientists call nucleation. High in the atmosphere, where the air is cold and full of moisture, a tiny particle drifts. It might be a grain of dust, a fragment of pollen carried up from the ground by a warm updraft months before, a fleck of sea salt from a distant ocean, and onto this particle, an extremely cold water droplet freezes. Just a few molecules at first, arranging themselves into that hexagonal lattice, building the first microscopic scaffold of what will eventually become a crystal. From that point, the crystal begins to grow. And the way it grows is through a process called deposition, where water vapor from the surrounding air attaches directly to the surface of the crystal and freezes. Not as liquid water, not as a raindrop, directly from vapor to ice, bypassing the liquid state entirely. This is worth pausing on for a moment because it answers a question many people have never thought to ask. Snowflakes are not frozen raindrops. They are not rain that got cold on the way down. They are built, molecule by molecule, directly from the air itself. What falls as sleet is frozen rain. What falls as snow is something else entirely. It is ice that has been assembled in the sky, piece by piece, from water that was never liquid to begin with. A snowflake is not frozen. It was never anything other than what it is. As the crystal grows, it develops faces. Flat surfaces, smooth and precise, each one a reflection of that underlying hexagonal architecture. At first, the snowflake is simple. A tiny hexagonal prism, like a section of honeycomb or a short pencil with 6 sides. Clean. Minimal. But then something happens. At the corners of that little prism, at the points and edges where faces meet, the geometry of growth changes. Water vapor molecules drifting through the air are more likely to encounter a corner or a point than a flat face. They land there more often. They build up faster. The corners begin to grow outward faster than the flat faces, and in doing so they create new surfaces, new edges, new corners for the next molecules to find. The crystal begins to branch. This is the moment where a simple hexagonal prism becomes something else, something more elaborate. The branches grow, and at their edges new branches appear, and at the edges of those, still smaller ones. The snowflake is building itself layer by layer in a process that is neither planned nor random, but something in between, governed by rules but shaped by circumstance. The resulting structure has a name. It is called a stellar dendrite. Dendrite comes from the Greek word for tree, and there is something right about that. A fully formed snowflake does look like a kind of microscopic tree. 6 trees growing outward from a common center, each one a mirror of the others. And they are mirrors of each other because they are all experiencing the same conditions at the same time. All 6 arms of a snowflake grow through the same air, at the same temperature, in the same humidity. What happens to one happens to all. The symmetry is not imposed from outside. It emerges from within, from the fact that all 6 arms are, at every moment, living the same life. In the winter of 1885, on a farm in Jericho, Vermont, a young man named Wilson Bentley carried a camera out into the cold. He was 19 years old. He had grown up watching winter, the way people who live in northern places do, with a mix of familiarity and deep, quiet attention. But Wilson Bentley had always looked more closely than most. He had been given a microscope as a child, and had spent years trying to sketch snowflakes by hand before they melted. He understood, even then, that each one was different. That each one was, in some sense, unrepeatable. The camera changed everything. Bentley had modified a bellows camera so that it could be fitted to a microscope, allowing him to photograph individual snowflakes at high magnification before they disappeared. The technical challenge was considerable. He had to work outside or in an unheated space to prevent the warmth of his body from melting his subjects. He had to catch the snowflakes on a dark surface, a piece of velvet or a cold wooden board, and transfer them to the microscope slide with the gentlest possible touch, using a feather or a thin splinter of wood. He had to work quickly, because even in the cold, a snowflake's finest details can begin to blur within minutes. And for every one image he captured that satisfied him, he had to examine perhaps 1,000 that did not. He was patient in a way that is difficult to fully appreciate. Patient not because he was resigned, but because he was genuinely absorbed. He loved what he was doing. He could spend hours in the cold examining crystal after crystal and feel that the time had passed pleasantly. Over the course of his lifetime, Wilson Bentley photographed more than 5,000 individual snowflakes. 5,000 unique, unrepeatable structures, each one assembled by the same invisible process, each one different from all the others. He published his work, and it reached people who had never thought to look at snow as anything other than weather. His photographs revealed something that words had struggled to convey: the complexity, the delicacy. The fact that something so common, so everyday, contained this much hidden geometry. He became known as the Snowflake Man. He died in 1931 at the age of 66 after walking home through a blizzard. It seems, in the way that certain facts do, exactly right. He spent his life in devotion to snow, and snow was there at the end. His photographs are still extraordinary. Looking at them now, nearly a century and a half after they were taken, there is something about the level of detail, the clarity of the branching, the precision of the symmetry that makes it difficult to believe they were captured on a farm in Vermont with equipment that no longer exists. He was, in the truest sense, an artist of attention. What Bentley's work demonstrated, visually and undeniably, was something that people had suspected but never quite proven. No two snowflakes are alike. Or at least, in all the thousands he photographed, all the millions he examined, he never found two that were the same. This is a claim that people sometimes push back against. Surely if you fall long enough, eventually shapes must repeat. Surely the number of possible configurations is finite. And in a strictly mathematical sense, this is true. Two snowflakes could, theoretically, be identical. No law of physics forbids it. But consider the scale involved. A single snowflake contains approximately 1 quintillion water molecules. That is a 1 followed by 18 zeros. The number of ways those molecules can be arranged, the number of paths through the atmosphere that could produce any given configuration, is so vast that the probability of two snowflakes being truly identical is, in practice, essentially zero. Not impossible. Just so unlikely that the difference between impossible and that is not worth arguing about. Each snowflake is, in this sense, a record. A physical record of the exact path it took through the atmosphere, the precise sequence of temperatures and humidities it passed through, the specific circumstances of its brief existence. It carries its history in its shape. You are, in some ways, the same. The particular shape of who you are right now carries the record of everywhere you have been. In the 1930s, in a laboratory in Japan, a physicist named Ukichiro Nakaya began to ask a question that no one had quite answered. Not Kepler, not Bentley, not any of the careful observers who had come before. He wanted to know not just what snowflakes looked like, but why they looked the way they did. What determined the shape? What was the relationship between the conditions in the atmosphere and the form that emerged? To answer this, he needed to make snowflakes himself. This was not a simple undertaking. Nakaya worked for years to develop a method for growing artificial snow crystals under controlled laboratory conditions. He constructed what were essentially miniature cloud chambers, sealed environments where he could precisely regulate temperature and humidity and watch what happened. He grew crystals on thin threads, on fine wires, in still air and moving air, at temperatures ranging from just below freezing down to the kind of cold that makes metal brittle. What he found was a map. Nakaya discovered that the shape a snowflake takes is exquisitely sensitive to the conditions in which it forms. Not just broadly sensitive, but precisely so. Small changes in temperature, shifts of just a few degrees, could transform the shape of the resulting crystal entirely. Near 0 degrees Celsius, just below the freezing point, water tends to form thin hexagonal plates. Simple, flat, like tiny glass tiles. Drop the temperature to somewhere between -3 and -10 degrees Celsius, and something entirely different emerges. Long, thin needles. Hollow columns. Shapes that look nothing like the branching stars most people picture when they think of snowflakes. Go colder still, down to around -15 degrees Celsius with plenty of moisture in the air, and there they are. These are the snowflakes of Christmas cards and paper cutouts, the archetypal form, and they appear at that specific temperature because of the way growth dynamics shift at that particular point in the phase diagram of ice. Drop further in temperature, colder still, and the shapes simplify again. Small plates. Columns. the elaborate branching retreats. Nikaya eventually identified more than 35 distinct basic shapes of snow crystal. Later researchers extended his classification to over 120 types, grouped into 8 main categories, each one the product of a particular temperature, a particular humidity, a particular set of atmospheric conditions, each one a signature of the cloud it came from. He published his findings in a book that became a foundational text in the study of snow. And he described snowflakes with a phrase that has stayed in the literature ever since. He called them letters from the sky. Each crystal, he said, carries a message about the conditions it passed through on the way down. If you know how to read the shape, you can read the weather. Think about that for a moment, lying there in the quiet. Every snowflake that has ever landed on your coat, on your upturned face, on the windowsill outside, was carrying information. Not in any mystical sense, but in a very literal one. Its shape was a record of the air it had traveled through, the temperature at each altitude, the moisture content of each layer of cloud, a tiny, intricate, ephemeral document written in ice. And then it melted, and the message was gone. Nikaya's diagram, that careful map of shape against temperature and humidity, is still used by atmospheric scientists today. It remains one of the most elegant pieces of experimental work in the physics of ice, a lifetime of patient observation translated into something genuinely useful, genuinely beautiful. There is something deeply calming, if you let it be, about the idea that the world is this ordered. That even in the apparent randomness of a snowstorm, precise rules are quietly operating. That chaos, looked at closely enough, turns out to be pattern. There is a shape in mathematics called the Koch snowflake. It was described in 1904 by a Swedish mathematician named Helge von Koch, and it is one of the earliest examples of what we now call a fractal. The Koch snowflake begins with an equilateral triangle. Then, on the middle third of each side, another smaller equilateral triangle is added, pointing outward. Then, on the middle third of each of the new sides, another smaller triangle. Then smaller ones still, and smaller ones again, and on infinitely, each iteration adding detail at a finer scale. The result looks remarkably like a snowflake. 6-pointed, elaborately branching, with smaller versions of the same structure repeating at every level of magnification. But the Koch snowflake has a property that sounds, at first, like a contradiction. Its perimeter is infinite. If you were to walk the edge of a Koch snowflake, following every branch and sub-branch and sub-sub-branch, you would walk forever. The boundary of the shape never resolves into a smooth line. There is always more detail, always another level of branching to follow. And yet the area enclosed by the Koch snowflake is finite. Perfectly, provably finite. A shape with an infinite perimeter enclosing a finite area. This is not a trick. It is a genuine mathematical fact, and it points towards something deep about the nature of fractal geometry, the geometry of shapes that repeat at different scales, the geometry that appears throughout the natural world. Real snowflakes are not perfect mathematical fractals. They have a limit to their branching, a smallest scale below which the crystal structure simply cannot subdivide any further. But they are fractal in spirit. The same pattern, the same logic of branching, repeating at progressively smaller scales. Zoom in on one arm of a stellar dendrite and you see smaller arms. Zoom in on those and you see still smaller ones. The structure echoes itself, not infinitely, but deeply enough to produce that characteristic sense of richness, of never quite reaching the bottom. This self-similarity, this quality of containing smaller versions of the larger pattern, is something the human eye and the human brain respond to in a particular way. Research into how people perceive fractal patterns suggests that we find them inherently calming, not just beautiful, but soothing. There is a theory, not yet fully established but intriguing, that our brains are attuned to fractal patterns because they are so prevalent in the natural world. The branching of trees, the patterns of river deltas, the shapes of coastlines, the structure of clouds. We evolved in a world full of fractals, and some part of us recognizes them as familiar, as safe, as home. When you look at a snowflake, or when you simply imagine one, you are engaging with a pattern that your nervous system has some ancient familiarity with. The mathematician, Benoit Mandelbrot, who more than anyone else developed the formal theory of fractals in the 20th century, described fractal geometry as the geometry of nature. Not the geometry of straight lines and smooth curves that we learn in school, but the rougher, richer, more detailed geometry of the world as it actually exists. Clouds are not spheres, mountains are not cones, coastlines are not circles, and snowflakes are not simple hexagons. They are something more patient than that, something that takes the simple rule of sixfold symmetry and elaborates it, branch by branch, into forms of almost inexhaustible complexity. Mandelbrot once said that a cloud is made of billows upon billows upon billows. A snowflake is made of branches upon branches upon branches. The same principle, the same deep grammar of the natural world. There are researchers today still working on questions that Kepler first asked on that cold bridge in Prague 4 centuries ago. The mathematics of snowflake growth is not fully solved, not even close. Computational scientists at the University of Wisconsin, Madison, and the University of California, San Diego, have spent years building computer models that attempt to simulate the growth of a snowflake from first principles. These models, called cellular automata, treat the growing crystal as a grid of cells, each one following simple rules about whether to freeze or remain liquid based on the state of its neighbors. When you run these models, something beautiful happens. The simulated crystals begin to look like real ones. The branching appears. The sixfold symmetry emerges. The variety of shapes that corresponds to different temperature and humidity conditions starts to reproduce itself on screen. But the models are still imperfect, still incomplete. There are aspects of real snowflake growth, particularly the way flat faces form and maintain their flatness during growth, that the models struggle to reproduce. The physics of the interface between ice and water vapor, at the scale where individual molecules are attaching to the crystal lattice, remains one of the genuinely hard problems in the science of ice. There is something almost comforting about this, if you are the kind of person who finds comfort in incompleteness. The snowflake, that small and quiet thing, that thing that lands on your sleeve and is gone before you can look at it properly, is still not fully understood. After 4 centuries of inquiry, after microscopes and cloud chambers and supercomputers and cellular automata, it still holds something back. In December of 2023, a researcher at the University of Utah named Jim Garrett published a study about how snowflakes move through turbulent air. Turbulence is one of the genuinely hard problems of physics, one of the few remaining areas where the equations of fluid dynamics have not been fully solved. Despite the complexity of the snowflakes and the chaos of the turbulent air around them, the way snowflakes accelerate through that air could be predicted using a relatively simple mathematical parameter. A single number, called the Stokes number, which describes the relationship between a particle's inertia and the forces of the fluid around it. Garrett himself remarked on the strangeness of this. He said that there is something deeper going on in the atmosphere that leads to mathematical simplicity rather than the extraordinary complexity you would expect from looking at complicated snowflake structures swirling in turbulent air. Order, emerging from what looked like disorder. This keeps happening with snowflakes. Every time someone looks carefully enough, they find more order than they expected, more precision, more quiet geometry operating beneath the surface of things. And perhaps that is the real gift of thinking about snowflakes late at night, when the day has done its work and you are lying still and the world outside is cold and dark. The reminder that order exists, that beneath the apparent randomness of things, rules are operating. Patient rules. Ancient rules. Rules written into the angle of a hydrogen bond, expressed outward through every crystal that has ever formed in every cloud above every winter landscape on this planet. The day may have felt chaotic. The things you are carrying may feel formless, heavy, resistant to any kind of structure. But somewhere in the cold air above you, water molecules are finding their angles. Crystals are forming. 6 sides, always 6 sides, because the mathematics leaves no other option. There is a particular kind of peace in that, if you let it arrive. Somewhere tonight, it may be snowing. Somewhere, almost certainly it is. High above some quiet field or sleeping city or dark stretch of ocean, crystals are forming on specks of dust and beginning their long, slow fall, each one tracing a unique path through layers of atmosphere, each one accumulating its history in its shape, each one a letter from the sky that no one will ever read. They are patient snowflakes. They do not hurry. They drift. The air around them is cold and still and vast, and they move through it at their own pace, turning slowly, accumulating their branches one molecule at a time, following rules that have been in place since before this planet had oceans. You have been watching over a great deal today, thinking about a great deal, holding a great deal. You can put most of it down now. It will be there if you need it. But you do not need it tonight. Tonight, if you like, you can just be a person lying quietly somewhere warm, while outside the world is cold and the geometry of water is doing what it has always done, without any help from anyone, without any need for attention or effort or understanding. The mathematics continues whether we watch it or not. The crystals form. The branches grow. The sixfold symmetry asserts itself, molecule by molecule, in the cold, dark air above sleeping towns. Han Ying noticed it 2,000 years ago and wrote it down and moved on. Kepler noticed it on a bridge and spent a winter writing about it and never found the full answer and was content with that. Bentley spent a lifetime in the cold, capturing images that no one had ever seen before, patient and absorbed and unhurried, examining 1,000 crystals to find one worth keeping. All of that attention, across all of those centuries, and the snowflake remains. Unchanged, unimpressed, still falling, still 6-sided. There is something in that continuity that is very restful if you let it be. The sense that certain things simply persist. That the rules of ice and water and cold air have been operating for longer than human worry has existed and will continue operating long after tonight's particular worries have dissolved. You are somewhere warm. The air around you is still. Whatever you are carrying today is already becoming a little more distant, a little softer at the edges, the way things do when sleep begins to approach. And so we leave it here, among the quiet geometry of falling things. Somewhere behind you, the day is already distant. The snowflakes are still forming in cold air. You cannot see, each one patient, each one precise, each one unique in a universe of simple rules. Drift now, if you are ready. Sleep well. There is something worth dwelling on in that word, deposition. The way water vapor moves directly from gas to solid, bypassing the liquid state entirely, is called deposition, and it happens because at certain temperatures and pressures the liquid phase is simply not available. The conditions do not allow for it. The water molecule arrives at the surface of the crystal, finds its place in the lattice, and locks in. No hesitation, no intermediate state. It goes directly from drifting freely through cold air to being part of something permanent. There is a kind of grace in that directness if you sit with it. The surface of a growing ice crystal is not perfectly smooth. Looked at closely enough, it is a landscape of steps and terraces, each step one molecule high, each terrace a flat face of the developing crystal. Water vapor molecules arriving at the surface tend to diffuse along it, moving across the flat terraces until they find a step edge, a place where they can attach to two surfaces at once rather than one, and there they settle. This is why the flat faces of a snowflake can grow so smoothly. The molecules are not landing randomly. They are finding the most stable available position, the one that allows them to bond to the most neighbors, the one that costs the least energy. In this sense, a snowflake is an extremely patient optimization. Every molecule finding the most comfortable available place, and in doing so, collectively building something of extraordinary complexity without any of them knowing what the whole will look like. There were others, before Bentley and after him, who devoted themselves to the close observation of snow in ways that are worth knowing about. A Scottish physician named Arthur Worthington, working in the 1870s and 1880s, became absorbed by the visual record of natural events. He is remembered mostly for his studies of splashing milk droplets, high-speed photography revealing crowns of liquid that the eye could never catch unaided. But Worthington was part of a broader movement of Victorian scientists who believed that careful looking, aided by the new technologies of photography and microscopy, could reveal hidden orders in the natural world. What Bentley understood, perhaps before he could articulate it fully, was that the snowflake existed at a scale just below ordinary perception. It was not truly invisible. You could see a snowflake, but you could not see what it was. The detail was there, waiting just beyond the threshold of the unaided eye. The camera and microscope together moved that threshold, and what was revealed had been present in every winter for as long as winters had existed. Billions of snowflakes falling on people who had no idea what they were looking at. He wrote about this occasionally, in the quiet, plain way of a farmer from Vermont. He said that under the microscope, I found that snowflakes were miracles of beauty, and it seemed a shame that this beauty should not be seen and appreciated by others. There is no grandstanding in that sentence, no performance, just a man who had seen something and wanted to share it. His photographs were eventually compiled into a book published in 1931, the year of his death, titled simply Snow Crystals. It contained more than 2,400 of his images, plate after plate of forms so varied and so intricate that the book still surprises people who encounter it for the first time. A single copy of that original edition, if you found one now, would cost more than most people earn in a month. Not because of the rarity of the object, but because of what it represents. A life's worth of cold mornings and careful attention pressed between covers. His negatives are preserved at the Smithsonian Institution. The images he made with a modified camera on a farm in Vermont over a lifetime of winters are considered part of the scientific and cultural heritage of the United States. They are treated, appropriately, like what they are, records of something that no longer exists, made by someone who understood that the world is full of unrepeatable things and that some of them deserve to be witnessed. Nakaya's laboratory in Hokkaido, Japan, was not the only place where people were trying to understand the relationship between snow and the conditions that produced it. In the Swiss Alps, in the mid-20th century, a researcher named André Vallon was working with meteorologists to understand how snowpack forms and evolves, how the crystals that fall from the sky are transformed by time and pressure and temperature into the dense, layered structures of a deep snowpack. What Vallon and his colleagues found was that snow does not simply accumulate and stay fixed. It changes. The crystals at the surface of a snowpack are exposed to wide swings of temperature, to the sun's radiation during the day and the intense cold of clear mountain nights. They sublimate, releasing water vapor into the air above, and then refreeze. They sinter, bonding to neighboring crystals at their points of contact. They grow new facets in response to the vapor pressure gradients within the snowpack, sometimes developing into large, loosely bonded crystals called depth hoar, which are beautiful to look at, but deeply unstable, the kind of structure that, in the wrong conditions, can contribute to avalanche. The snowpack, in other words, is alive, not biologically, but dynamically. It is constantly changing, constantly responding to its environment, constantly moving through states that no one who had not looked closely would ever suspect. There is a group of scientists now called snow hydrologists, and their work involves understanding how the water stored in mountain snowpacks will eventually flow into rivers and reservoirs, how the timing and volume of that flow will affect the water supply for the cities and farms that depend on it. In the western United States alone, the snowpack in the Rocky Mountains and the Sierra Nevada provides water for tens of millions of people. Nakaya's map of crystal shapes, that diagram of form against temperature and humidity, turns out to be practically useful in ways he may not have anticipated. When atmospheric scientists measure the type of snow crystal falling in a given storm, they can infer something about the temperature profile of the cloud that produced it. When radar instruments detect the orientation of falling crystals, they can deduce information about the winds within the storm. The shape of a snowflake, that thing Kepler puzzled over on a bridge in 1610, is now part of the toolkit of modern meteorology. The question that seemed purely aesthetic, purely philosophical, purely the kind of thing a curious astronomer might wonder about on a cold evening, turned out to have practical applications that extend through centuries of subsequent science. Benoit Mandelbrot was born in Warsaw in 1924 and spent much of his life working at IBM's research laboratories in New York, which was an unusual setting for a mathematician interested in pure geometry. But Mandelbrot was never quite a pure mathematician in the traditional sense. He was interested in the shapes of things in the real world, the roughness of surfaces, the irregularity of coastlines, the turbulence of fluids, the fluctuation of financial markets. He wanted a mathematics that could describe the world as it actually appeared, rather than the idealized smooth world of classical geometry. The Koch snowflake, that mathematical object described 40 years before Mandelbrot began his work, was one of the early examples of what he would eventually call fractal geometry. He gave the field its name, from the Latin word fractus, meaning broken or irregular. And he argued with considerable force that the natural world is not smooth, that the idealized geometry of Euclidean shapes, the circles and spheres and cones, was a useful abstraction but not an accurate description of what actually existed. A real coastline, Mandelbrot pointed out, does not have a fixed length. The length you measure depends on the length of your ruler. Use a long ruler and you miss the small indentations. Use a shorter one and you capture more detail, but miss the smaller irregularities within each indentation. Make your ruler shorter still and more detail appears. The coastline never resolves into a smooth curve. There is always more roughness at smaller scales. This is the fractal property, and snowflakes, as Mandelbrot noted, share it, at least down to the molecular level. Each branch contains smaller branches. Each smaller branch contains still smaller ones. The pattern repeats across scales in a way that is not perfectly self-similar, the way a mathematical fractal is, but is deeply analogous to it. Researchers studying how people respond to fractal patterns have found some intriguing results. A physicist named Richard Taylor working at the University of Oregon, has spent years measuring what he calls the fractal dimension of various visual patterns and correlating it with people's aesthetic and physiological responses. He found that patterns with a fractal dimension in a particular range, roughly between 1.3 and 1.5, tend to produce the most positive responses. They are found most beautiful, most calming, most restorative. Snowflakes fall within that range. So do many natural landscapes, many patterns of leaf venation, many river systems. The human visual system, Taylor argues, is tuned to these patterns because it evolved in environments full of them. We are, in some deep sense, at home in fractal patterns. They feel right in a way that is difficult to articulate, but easy to feel. There is a particular quality of attention that fractal patterns seem to invite. Not the sharp, focused attention of solving a problem, but the soft, wandering attention of looking at a landscape or watching water or lying somewhere comfortable while words arrive and drift away again. The eye moves through the pattern, finding detail at every scale, never quite reaching a stopping point. And in that movement, something in the nervous system settles. This is sometimes called soft fascination in the literature on attention restoration theory, a field of environmental psychology concerned with how different kinds of environments and stimuli affect mental fatigue and recovery. Hard fascination is the kind that demands concentration, that requires you to track and respond. Soft fascination is the kind that holds your attention gently, without effort, without any requirement to do anything with what you notice. Natural environments, fractal patterns, the sound of water, the movement of leaves in wind, all produce soft fascination. And soft fascination, the research suggests, is genuinely restorative. It allows the directed attention system, the part of the mind that works hard all day, to focus and decide and respond, to rest. Looking at a snowflake or imagining one, or simply letting the idea of one drift through your mind is a small act of soft fascination. And perhaps that is why it is such a natural thing to think about at the end of a long day, in the quiet, when the mind is ready to release its grip on the day's particular demands. There is a researcher in Japan, a glaciologist named Yoshinori Furukawa, who has spent decades studying the growth of ice crystals at temperatures so low that the crystals form shapes that most people have never seen. At temperatures below -40 degrees Celsius, ice grows into forms called bullet rosettes, clusters of hexagonal columns radiating outward from a central point like the petals of a frozen flower. They appear in the very high atmosphere, in thin cirrus clouds far above the weather that affects daily life. And they scatter light in ways that produce some of the more unusual optical phenomena that occasionally appear in the sky. Halos around the sun, arcs of color at the horizon, pillars of light above street lamps on very cold nights. These phenomena have names. The 22-degree halo, the most common, appears as a ring of light around the sun or moon caused by the refraction of light through the hexagonal faces of ice crystals. The sundog, or perihelion, appears as a bright spot to the left or right of the sun, sometimes with a faint tail of color. The circumzenithal arc appears as a curved band of color high in the sky, sometimes described as an upside-down rainbow, and it is among the most beautiful atmospheric effects that most people have never noticed. All of these are caused by the hexagonal geometry of ice crystals. The same geometry that Kepler puzzled over, the same geometry that traces back to the angle of a hydrogen bond, is responsible for these lights in the sky. The crystals are too small to see individually, too high to feel as snow, but their collective geometry bends light and sends it back to Earth in these quiet, unexpected displays. The next time you see a halo around the moon on a cold night, you will know what you are looking at. You will be seeing the six-fold symmetry of water operating at a scale you cannot see, writing itself in light across the sky. It is the kind of thing that is easy to pass by without noticing. and equally easy, once you know it, to find very beautiful. Furukawa's work and the work of others like him has contributed to a much more detailed understanding of how ice surfaces behave. The interface between ice and the surrounding air or water is not the sharp, clean boundary it appears to be at larger scales. At the molecular level, the surface of ice is a strange and somewhat disordered place, a quasi-liquid layer where the molecules are neither fully organized into the crystal lattice nor fully free the way liquid water molecules are. This layer, sometimes called the premelting layer, was predicted theoretically long before it was observed, and its properties turn out to matter for a surprising range of phenomena. It is part of why ice is slippery. It is part of why snowflakes can sinter and bond to each other in a snowpack. It is part of why the growth of a snowflake surface proceeds the way it does, with molecules finding their way to step edges rather than landing randomly on flat faces. The surface of ice, at the scale where it matters, is subtle, not the clean, hard boundary we imagine. Something softer and more complex, something that is still not fully characterized even now. There is something gently reassuring in the image of that surface, the idea that even the boundary between solid and air, between the crystal and the world around it, is not a sharp line but a gradual transition, a zone of something in between. Not quite one thing, not quite the other, just a soft, unhurried interface doing what it has always done. The night is like that too in some ways. Not a sharp boundary between the day and sleep. A gradual transition, a slow softening of edges. The thoughts becoming less insistent, the sounds becoming more distant, the body becoming heavier and more still. You do not need to cross any line. You do not need to arrive anywhere. You are already in the transition, already in that quiet zone between one state and another, and you can simply remain there for as long as you like and let the rest take care of itself. The snowflakes are still forming. High above whatever is outside your window, in air far too cold and thin to feel, the water molecules are finding their angles, locking into their hexagonal lattice, building their six-fold structures one attachment at a time. Patient. Unhurried. Governed by rules older than any question anyone has ever asked about them. They do not know they are beautiful. They do not know they are unique. They do not know that someone 2,000 years ago noticed their six-sided nature and wrote it down, or that a man in Vermont spent a lifetime in the cold trying to capture their image before they disappeared, or that a physicist in Japan mapped their shapes against temperature and called them letters from the sky. They just fall. Slowly. Through cold, still, dark air. And that, in its own quiet way, is enough.